Hello and welcome back to our introductory R programming course. In this module, we will be covering R graphics, that is making plots and visualizations of your data. In particular, we'll be covering what people call base R graphics, but don't be fooled by the name. Base R graphics are extremely powerful and customizable and allow you to make really eye-catching and professional looking graphics. Let's get started. Okay, today we're going to be talking about R graphics, that is plotting data using data visualizations in R. Now we're going to be talking about what people refer to as base R graphics. Even though it says base in the word or basic in the word, this is an extremely powerful graphing capability. You can make really high quality plots if you understand all the different things you can customize in your plots. Okay, so we're going to be playing around with a few data sets. The first one is the Ames housing data. So I'm going to read that in. I'll have links to this in the description. As you can see, I'm in my video code directory. So to get to this data set, I have to go up one directory and then back down into data sets. And I've called it ameshousing.csv. And to make the plots a little bit easier to read, I'm going to subset the data. First, let's take a look. One of the columns is neighborhood. The data set's pretty big, so dim Ames. So when we go to plot things, there's 2,930 rows. So when we go to plot things, there's just a lot of points. So I'm going to subset the data to make it smaller and easier to see what's going on. So I'm going to subset it to just the North Ames neighborhood. So the way I'm doing that is I'm using the Ames dollar neighborhood variable, and I'm checking for equality with North Ames. And I'm taking Ames. I'm selecting those rows for which the neighborhood equals North Ames, and then I'm keeping all the columns. So if I do that, and I do dim Ames, now it's much smaller, 443. Okay, so let's, we've already seen how to make a plot, so let's just go through this. So I'm going to plot the sale price against the size of the house in square feet. So the size of the house is in the variable grLiveArea, and the sale price is sale price. And I'm going to plot it in thousands. So I'm going to go ahead and divide that by 1,000. And then one of the great things about R, it's like super simple to make a plot. I just do plot XY, and now I have a plot. Now in RStudio, that plot will show up in this panel. If you have things set up the same way as I do, this panel is in the bottom right. There's various tabs here: files we've seen before, and plot and help we've seen before, and now we're looking at the plots tab. So just in this one line of code, plot XY, it makes a reasonable plot. There's lots of things we'd like to improve about this plot, but it's pretty good to start. Okay, so the first thing I want to go over is what actually happens when you make a plot. So what's actually getting called is plot.default. So if we look at the source code, it looks like this. So if you look at the source code, it's kind of setting up a bunch of things: X labels, coordinates. So what we're going to do is we're actually going to run through this, and I think this will give us a little bit more insight about what's happening when R makes a plot. Okay, so what I'm going to do here is I'm going to use the debugging tool, debug plot.default. So we haven't gone over the debugging tool. We're not going to go over it today. I'm just using this for illustrative purposes so that we can, basically what the debugging tool allows you to do is to run each lines of code inside of a function and see what gets produced. So this is actually it's just to get on like a slight tangent here. The debugging tool in R is really, really cool. We're not going to cover it in this set of videos, but it's something as you get more and more advanced as an R programmer, this is something you really want to learn how to use. Okay, so plot x, y. You can see what happens here is it pulls up that source code for the debug function, and then the the prompt in the console changes. So if I press next, it basically will run through the lines of this function one by one so we can see what happens. All right, so this one, it's setting up an axis. It's setting up local box, which is going to be related to the box that's around the plot. Sets up the window. Makes an X label. So one of the cool thing about the debugger is that I can now type in like X label and you can see the label it's going to apply. Y label, XY. XY is the output of the xy.coords function. This basically holds the data and the labels. So these are the X values, the sizes of the houses in square feet, and these are the sale prices in thousands of dollars. Okay. Setting up labels. XLim. So XLim is the limits of the x-axis. So it runs from 715 square feet to 3,112 square feet. Same thing for YLim. Okay, now here's where the cool stuff starts happening. So the plotting in R works on what are called graphics devices. So what it's doing here in these few lines of code is it's setting up the graphics device. And it's this on.x, what's that doing? It's telling what's going to happen after the function is done, which is to flush the graphics device. And then here's where we start. So plot.new, what that does is that opens an empty graphics device. So that's this here. This is called a graphics device. There's various graphics devices. We'll talk about other ones. This is basically the graphics device which prints to the screen so that you could see things. We'll see later on there's graphics device that prints to file so you can save your plots. Okay, and then let's see, local window, panel first. Okay, so plot XY, this is where it's going to draw the plot. So that is putting the points on the plot. And the reason I want to emphasize this is plotting kind of happens in successive steps in R. It doesn't like generate the whole thing at once. So what it's going to do, it's going to put the points down, it's going to put the axes down and the labels down and all that stuff. Okay, if axes, so if it wants to draw axes, and axes is true, so it is going to run this code. First it draws the x-axis, that's what it looks like. Then it draws the y-axis. Then it puts a box around it. And then it adds the annotations. So the label for the x-axis and the label for the y-axis. And then it exits the function. So the point of showing you all this is that it doesn't all happen at once. I mean, it does all happen at once when you call a function like this. But what's going on underneath is it sets up what's called a graphics device, and then it adds things to it successively. So when you get to doing more and more advanced R plots, you're going to want finer and finer control of every piece that goes into a plot. And that's the way you're going to be creating your plots, basically adding things one at a time with various different functions. Now to make sure we don't always invoke the debugger every time we call plot, we have to undebug plot.default. Otherwise, every time we call plot, it's going to go through that thing, and we don't want to have to mess with that now. Okay, now virtually every aspect of these plots is customizable. So the documentation for the things you can customize is spread out in a few different places. So we'll show you some of them. So if I go to the plot documentation, you want to select generic XY plotting, and let's make this bigger. So the first thing it says here is for simple scatter plots, plot.default will be used. Plot is an example of what's called a generic function, which means that it looks at the arguments and then selects a specific function. So plot is the generic, and plot.default is one of the specific ones it'll select. There's some things documented here, but they're actually documented in a little bit more detail in plot.default. So let's pull that up. Okay, so you can see this is a draw a scatter plot with decorations such as axes and titles. X, Y, you know what that means. These are the X values, these are the Y values. Type equals P refers to what type of plot you're going to make. So P is for points. We'll look at that a little bit further down. You can control the limits of the x-axis and the y-axis. If you remember back when we were debugging plot.default, that was one of the things it used. You can do a log transformation. You can set a title with main. You can do a subtitle. You can control the labels on the x-axis, the labels on the y-axis. And I forget what and does. And logical value indicating whether the default annotation should appear on the plot. So sometimes you'll want to add all these different components like the axes and the labels yourself after you set up the plot. So you could do and equals false to make sure it doesn't do that for you, so you can set it up yourself later. Same thing for the axes. This stuff we're not going to look at. You can set an aspect ratio, so on and so forth. Okay, so what I recommend is reading through this. It'll take you a bit of time to read it, but then you'll at least have some exposure to the things you can change. The thing is, you're not going to know in the future the things that you're going to want to change. So it does make sense at the start, just spend some time reading. And in the future, if you think, oh, I would like to do this with my plot, you might bring forth a memory of, oh, I thought I read something like that in the documentation, and you'll go look for it and figure out exactly what you're supposed to do. So spend some time reading. There's also things like graphical parameters. We'll look at these in a little more detail. This is not an exhaustive list. There's another place in PAR where these are documented. Okay, so let's just play around with some of a few of these things that we can customize. So let's do plot XY. This was our default plot. But we should label the axes. So by default, what it does is it just takes the name of the variable. But we should probably say, xlab equals house size. Ylab equals sale price. And that's going to be in thousands of dollars. And now we're off the page, so let's organize ourselves. And maybe we want to have a title as well. Main equals North Ames housing data. Okay, so if we run that, now we get a little bit nicer plot here. All right, other things you can change. Let's see, you can change, all kinds of stuff. So let's just do plot XY. I'm not going to retype in all these labels, so you already know how to do that. PCH controls the plotting symbol. You can go from, I think it's 0 up to 16. So I'm just picking 2. You can make the points a different color, and you can make them a different size. So CEX, there's a bunch of things like CEX dot axis. So CEX generally controls the size of things without any extra letters here. CEX just means the size of the plotting symbols, and it's relative to 1. So 0.5 means half the size. We'll do it in a second with 2 to make it double the size. Okay, so this PCH equals 2, selected triangles. Col equals blue, made them blue. CEX equals 0.5, made them smaller. We can make it larger. So generally, if you have a lot of points, it makes sense to make them small so you can see them. So for this one, I probably would select 0.5 so you can see what's going on. Modifying the plotting symbols can be really useful for getting more information into the plot. So let me show you an example of that. So say one of the variables is the number of cars in the garage. So if I wanted to get that information into the plot, I might want to change the plotting symbol depending on how big the garage is and the number of cars that it holds. So let's do that. So let's say, and actually let's first look table Ames $garage cars. Okay, runs from 0 up through 4. So we're going to have 5 different plotting symbols, and I'll just do, well, let's just do 1 through 5. Okay, and let's set up the basic plot first. Okay, so this is the plot we saw before. But basically, I want to change PCH to depend on how many cars are in the garage. So the cool thing about some of these arguments that you can modify, you can give them a vector. So basically, I want to give it a different value of PCH depending on what the garage size is. And here's a little trick that allows you to do it. So the garage sizes are 0 up through 4. So I can do the following. Let me just type it out and I'll explain what it's doing. Okay, so the first thing it's doing is taking garage cars and it's adding 1 to them. That's because the values are 0 through 4. So if I add 1 to every value, then the values become 1 through 5. And then it's putting that as the index for this vector I created, PCH's, which is 1 through 5. And so this is using the fact that you can repeat indexes when you index a vector, and it will, let me show you this step by step, because this is actually a pretty cool trick. All right, so here's PCH's. If I were to do PCH's 3, I get 3. If I were to do PCH's, 3, I get this. Actually, let's make this more interesting. Let's do, we really don't need to do this unless we're have different values. So 0, 1, 3, 4, 6. Okay, so if I do PCH's Ames $garage, all right, let's do Ames $garage cars. Here's the first 10 values. And if I do PCH's Ames $garage cars plus 1, so the first one becomes a 3. Ames $garage cars plus 1 is 3, so it grabs that one. Ames $garage cars 1 becomes a 2, so you get this one. So you can index these things in this way. Okay, so that gives you a different plotting symbol for each number of garage. Now, if you're looking at this plot, if you show this to someone, they're not going to know what those symbols mean, so you should give it a legend. And there's a function called legend, and the first argument is where you want it to go, so I'm going to put it in the top left. And then you have to tell it what you want to put in the legend. So I want to put the PCH values, and I have to put the garage sizes in, so that's 0 through 4, and I can give it a title. Okay, so that tells us what each of these plotting symbols mean. And notably, there's a house here, pretty big house, with a 4-car garage, whereas these are 2-car, 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 3-car. Okay, so that's showing you that you can make these arguments to plot be a vector. So this creates a vector of different PCH values depending on how many cars are in the garage. And it will notate the plotting symbols accordingly. So this is something you should really think about when you're making your plots, is to try to cram information into them. So a great plot will not be overwhelming, but it will be something that a person can kind of stare at for a while and glean more and more information out of it when they stare at it for a while. And this sort of accomplishes that. You can do the same thing with color and other attributes of the plot. All right, next thing I want to show, which is related, there's various different functions for adding things to the plot, one of which is you can add text to the plot. So you can actually make the plotting symbols be whatever you want by putting text at the points. So let's set up the plot again. Okay, so that's our basic plot. Now, what I want to do is I want to replace these circles with the number of cars in the garage. And the way it works, as I explained before, is that you add things to the plot. So there's actually no way to, once you put the circle on it, there's no way to take it out. But there is a way to set up the plot without putting the circles down. And that's to say type equals n. So if you do that, it sets up all the axes the way you want them to, but it doesn't put anything there. And then I can go in and I can add the text. So I can say there's a function called text, which is for adding text to the plot. The first two arguments are the XY values of where you want to add the text. And then the third thing is the text that you want to add. So I want to add the garage cars. So I can run that. And it sets up the same thing. It does a scatter plot, except the thing that gets plotted is the number of cars. And you can see here's the 4, here's the 2s and the 3s that we saw before. And you might decide, okay, this is a little bit too big. Maybe I should make this a little smaller. Oh, good point. So as I said, you can only add things, you can't take things away. So what you have to do if you want to change something in the text, you have to call plot again. Remember when we looked at the documentation, the first thing it does is it kind of sets up a new plot. So whenever you call plot, it will generate a new plot. So it's like starting over. And then many of the other plotting functions are designed to go on top of an existing plot, and text is one of them. So that does the same thing. It makes them, but it applies CEX equals 0.8, making them smaller. There's a bunch of other functions that operate just like text that allow you to add things to the plot. You can add polygons, rectangles, segments, arrows. Abline is a really common one, which allows you to input an intercept and a slope and add that to the plot. Okay, and we're going to look at lines later on to add lines to the plot. All right, one thing you can do is you can plot multiple plots on the same graphics device. So the way you do that is you do par mf row, and then you say how you want to lay out the plot. So if I want a 1x2 array of plots, which just means 2 plots side by side, 1 row, 2 columns, I do this. And then I can make my plot. So I'll do living area, sale price in thousands, and then I'll do another one, but instead of living area, I'll do year built. Okay, so normally what would happen is if I don't run this line, normally what would happen is I do this, and plot is a function that doesn't add to a plot, it generates a new one. So if I do that and then I run this, it'll replace it with this one. However, if I run this first, I'm telling R that I want a 1x2 layout or array of plots. And so when I call this, it'll put it on the left side to make room for both of them. And then I call this, it will put it on the right side. So this is what I mean by a 1x2. There's 1 row of plots and 2 columns. If I had done this, it makes room for 4 of them. So I can call this again, and it'll do 4 of them. But we don't want 4, we just want 2. Okay. Now, if I want to make a new plot, say I decide, now I want to make a plot with just living area. It's going to remember that MF row was set to 1, 2, and it will think I'm generating a new one with the same layout. So if I want to clear that out, I can either, there's a few different ways to do it. I can clear the plots here with clear all plots. I could reset this, so I could do this to make it a 1x1 array, and that will do what I want. I can also call dev.off. That will clear the plots. And then I could do it, make the plot. Okay, so there's various ways to unset the graphical parameters. You can set them back to the previous value. You can clear them by clicking that button, or you also clear them in code using dev.off. Okay, so this was our first instance of using the par function. Par is for setting graphical parameters. So let's look at the documentation. And so this is the most complete piece of documentation for listing out all the things that you can customize in a plot. So what I recommend doing is reading through this thing. Even though it's pretty long, you'll learn a lot. All right, so the description, we're not going to read through the whole thing, but I'll show you some of them. Par can be used to set or query graphical parameters. Parameters can be set by specifying them as arguments to par in tag equals value form. So that's what we did here. That's the tag, that's the value. Or by passing them as a list of tagged values. And then the usage is you could put them in par with tag equals value form, or you can put them in as arguments to a high-level plotting function. So a high-level plotting function is, for example, the plot function. So we set, for example, we set the, where's an example? Okay, so here we set, here's tag equals value, but we did it inside the plot function instead of inside of par. So some of the graphical parameters you can set inside of what's called the high-level plotting function. Plot is just one example. We also set color and CEX there. Okay. All right, so let's look through some of the other documentation here. Blah, blah, blah. I'm running through this fast, but you should read this. Oh, let's not skip this actually. Several parameters can only be set by a call to par. So things like the margins, we'll do that in a minute. Things like MF row, which we already did, can only be set by calling to par. The remaining ones can be set as arguments to high-level plotting functions. For example, well, these are some examples of high-level plotting functions. Okay, now here down below it lists out all these graphical parameters. So you can do things like set the background, CEX is for size, and then there's specific things whose size you can set, colors of specific things, so on and so forth. We'll look at a few of these. But this is a big long list of things. This is why I say that our plots are highly customizable. You can change all these different things to make the plot look exactly like you want it to look. Okay, let's pause here because we're going to do this in a minute. You can set the margins of the plot. So I usually do that with the mar parameter. And basically you give a length for vector of numbers. The first vector sets the size of the bottom margin. Second is the left side. Third is the top. And fourth is the right side. And this is the default value for that vector. So if you want to make we'll do this in a second. If you want to make the top margin smaller, you would do mar equals C5, 4, and then some smaller number than 4, maybe 2, as the margin size. Okay, we saw that. I'm not going to go through all these, but you really should read these at some point. Okay, let's use some of these. We did MF row. Let's do par family equals serif. So one thing, if I use this one a lot actually when I'm writing academic papers, is usually when I write the paper, the font in the document, the body of the text of the paper is usually in something like Times New Roman, which is a serif font. And by default, our plots don't have serifs. And so what happens if you just use the default font family, the font in the plot looks a lot different than the font in the body of the table. So I like to set family equals serif in my plots. And then when I do plot, then I get serif fonts in my plot. I think this looks a little bit nicer, especially if it matches the more closely matches the font in the body of the document you're working on. Let's see. Okay, dev.off will reset that. You can do margins. So let's do plot aims $. Okay, so that's the default. So this particular plot doesn't have a title. So maybe I want to make this smaller because this is just kind of wasted space if there's no title on the top. So let me just say that the default is this value. So that will reproduce this. Now if I change this, remember it's bottom, left, top, right. And it's really the default values over those values plus 0.1. I don't know why they do that, but that's what they do. If I wanted to make the top margin smaller, I would change this 4 to a 2. Oh, what did I do? Oh, MF row is not what I want. I want mar. Sorry about that. Okay, mar is the argument. Okay, so that makes that smaller. Let's see. You can, just to show you can change the other margins. Say I want more space on the right side, I would do that. That puts more space here. Okay. Let me just do quickly. You could do a lot with colors in R. There's a function called colors which tells you the default value. So let's see. Let's grab this. Okay, so if I do colors, this will print out all the named colors in R. There's a lot of them. There's 657 of them, apparently. We've used things like blue, but there's lots of different blues and all different types of colors. So, okay, let's do tomato 4. One of the cool things about the new version of RStudio is actually tells you what the color is when you type it in. So that's tomato 4. That's tomato 1. Okay, that's a nice color. So let's plot. Okay, so that's tomato. So there's a bunch of colors which have names. You can also get even finer detail. There are ways to set the colors by setting like an RGB value, if you're familiar with that. And there's other ways to do it. HSV. You can also specify colors with their hexadecimal codes, if you're familiar with how to do that. Okay, so there's lots of ways to change colors. Okay, so here we have a plot. Let's get a nice plot. Let's do this one. There's various ways to save your plot. So if you're working on something for a presentation or for a document report that you need to turn in, you're going to want to save your plots and put them in a Word document or LaTeX document or PowerPoint presentation. So there's various ways to save it. So I can click here, export, and save as image. I can give it which image type I want to save it as, depending on what I want. The default is PNG. I can set the aspect ratios. So if I want to make it square, I would set these to be equal to each other. And then I can give it a name and then click save. So that's one way to do it. You can do it in a bunch of different file types. You can also do it as a PDF. So you can save your plots that way. I actually don't recommend doing it that way. You can also save your plot using code. And that's the way I recommend doing it, because if you want to come back and change something about your plot, if you've saved it in code and you've saved your script for saving it in code, you could just go back and modify the code and change the plot how you want it. And you don't have to go back in and click a bunch of things and like remember what aspect ratio you picked and all that stuff. Okay, so this is how you do it. So as I mentioned before, our graphics work by setting up what's called a graphics device, and then it draws on the graphics device. And the only graphics device we've been working with so far is the one that prints to the screen. So that's just one of many types of graphics devices in R. There are graphics devices, most of the other ones are for writing to a file. So there's a graphics device, for example, called PDF, which takes a file name in, because you're going to write to a file. So say I want to save this in plots ameshousing.pdf. You have to give it the width and height in inches. And you have to draw the plot. So I'm just copying this. And then you have to close the graphics device. And you close it with dev.off. Okay. So normally, so if I don't call PDF, if I call this, it draws the plot over here. Now, if I call PDF first, what happens is it opens the PDF graphics device, and then any subsequent plotting commands, such as this one, are plotted to the PDF graphics device, which is not on the screen, it's a file. And then to finish, I have to close the PDF graphics device with dev.off. And what that does is it saves the file. So if I go into Files, here I was in Video Code, and I go up and down into Plots. There's now a file called ameshousing.pdf, which was just saved. And that's my plot. So now this is a file. It's like on my computer, I can take this and import it into other programs. So for example, if I like this plot, however, I don't want it to be so wide. I want it to be like taller relative to wide. I might make the height 7 instead of 5. So it's very easy to change. I just rerun this code. It resaved ameshousing.pdf, and now it looks like I want it to look. So this is the way I recommend doing it. It makes it really easy to go back and recreate your plots if you need to recreate them, and to modify them without having to go in and click things and remember things that you clicked before. Everything is saved right here. So if you're making professional plots for important presentations and documents and reports, I really recommend saving them in this way using the built-in graphics device. So we've just used PDF. You can also save it as an image like a PNG or JPEG, and then there's other types. PDF is really nice because it's what's called vector graphics. And the cool thing about vector graphics, let me open this up, is I can zoom in kind of like infinitely and it doesn't get blurry. So that's zoomed into 400%. It still looks really good. So that's one of the benefits of vector graphics like PDF. All right, now that we've learned a lot about plotting, let's put them to use and see another example. So I have a data set of weather data from Ithaca, New York. Again, this will be in the description. You can download this yourself. All right, so the U.S. government operates something called the U.S. Climate Research Network, and it's a bunch of really high-quality weather stations spread out around the United States. And there happens to be one just outside of Ithaca. And I've taken the data and I've cleaned it up a little bit and subsetted it to just the things that we want. So there's a column for the date, the hour of day, air temperature, and then there's a bunch of other stuff like precipitation, solar radiation, humidity, and soil properties. All right, so this data is reported every hour, and basically what I want to do is, the first thing I want to do is I'm going to be plotting the temperatures against time. But if you do, let's say class if $date. This is read in as an integer. And so the format is year, month, day. So this isn't really an integer. So I need to convert it to date format. So let me go through how to do that. All right, so if $date, I'm going to redefine as.date. And I have to make it a character. So you can always coerce to a higher type. So a character is a higher type than integer, so you can always do that. And then I have to tell it what format the date is in. And for doing that, there's all these codes that are set up. We're not going to go through this in detail, but basically the way this date is represented is a 4-digit year, so that's represented by %y. A 2-digit month, that's represented by %m, and a 2-digit day, which is represented by %d. Now, if your dates have slashes in them, you would do this. If they had hyphens, you would do that. But our date doesn't have any delimiters, so we just put them next to each other. And now if I do class if $date, it does that. And things like, okay, if $date 1, this is the date format is kind of cool. So I can like add to them and it gives me the next day. If I wanted to subtract, if I want to add 30, it gives us the next month. Whereas that operation wouldn't work if you had worked on this. If you had 30 to this, it would be 2004-10-57, which isn't a date. Here it gives you the right date. Okay. We're also going to be using the year. And the way we're going to get the year is we're going to use the format function. So format if $date, which is now a date class. And I just want to return the year. This is going to return it as a character, but I want it to be a number. So we may want to do some operations on this. So I do as.numeric. So character to numeric doesn't always work, but this will just return for example, the character string 2004, and R knows how to convert that to a number. We're also going to want the month, as I'll show later. So it's the same thing. Actually, let me just copy and paste. Grab the month. We're also going to want the day of the month. So we're grabbing that. We're also going to want, what else? The fractional day. Ooh, and I have a typo. If $day. If $day plus if $hour. The hours are represented as like military time. 1700 means 5 p.m. Let's see what's going on here. RStudio thinks there's an error. Maybe there is. Oh no, went away. We're also going to we might want this. So the DOY is for day of year. For grabbing the day of the year from the date, the code is %J. And we also may want fractional day of the year, including the hour. Okay, so these are some variables we're going to use. Hopefully no typos or errors there. And okay, let's make a plot. So I want to plot all the data from January of 2023. So I'm going to have to subset the data. And this is why I made these variables. If $year equals 2023, and if $month equals 1. I'm going to grab the fractional day, so it's the day plus the hour. And I'm going to plot the temperature in Celsius, so I'm grabbing that. And our plot X, Y, day of January. Y label is temperature in Celsius. Okay, so let's run this and this, and we got an error. What happened? Okay, let's see if we can debug this. X is all NA. That's no good. Okay, we made an error. So let's try to figure this out. There's II. Those are missing. Okay, so there's something wrong. Ith $year is all NAs. So what is the problem? Ith $date was okay. Oh, it didn't like that. All right, maybe we just ran it twice and that messed it up. Oh, I think what happened is after I converted it to a date, I tried to like reconvert it to a date and it messed it up. Maybe that messed it up. I don't know. Works now. Okay, so this is the plot of temperature against the day of January. And okay, so this is pretty good. It's every hour for the month of January in 2023. However, this kind of plot, each successive point is, it's a successive point. So really, you should probably connect them with a line. So it's probably better to do a line plot. So you could do a line plot with type equals L. And maybe that looks a little bit better. You can see here that there's a break here. I think that's because there are some missing values in the data. I don't think it's going to look good. If you wanted both points and lines, you can do type equals O. It looks okay. Maybe it's a little bit too busy. So I think I'll prefer type equals L. Okay. All right, so that's a basic plot. We're using type equals L to do lines instead of points. And that's the data from January 2023 in Ithaca. All right, one thing to know. One thing about winter temperatures is, normally it's warmer in the afternoon than it is in the morning. That's true most of the year. But that's called a diurnal cycle. The diurnal cycles are much stronger in the summer than in the winter, at least in a place like Ithaca. So you actually don't really see, kind of just does whatever it wants to do. Whereas if we were to plot, all right, let's do July actually, just to show you what this looks like. You see things kind of go up and down more regularly. Not only are the temperatures higher, but there's more of a daily cycle in July than there is in January. Okay, that's your bit of weather knowledge. Okay, so what I want to do next is I want to make a plot. We have data going back to 2004. I think it goes back to actually we can check. Head ith. The earliest data is October of 2004. So we can plot January temperatures from 2005 to 2023. So that's what I want to do. Okay, so let's do that. Years. And the way I'm going to do this is I'm going to set up an empty plot. So I could just put anything I want there. But I'm going to do type equals n for doing empty plot. I'm going to set up the x limits, y limits. Let's look at what they should be. well, this is just 1 year. I want to do all years. So maybe I'll be conservative and I'll do like minus, I mean, how cold can it get? Let's do minus 30 to 30. Probably doesn't get that warm, but we can go back and modify that. X label is day of January. Y label is again temp Celsius. And let's make this look nice. Okay, so that sets up an empty plot with the limits that we want. And the way I'm going to generate this plot is I'm going to loop over the years. That's why I created this years variable. And for each year, I'm going to add a line for the data for that year. Okay, so I need a for loop. And I need to select, let's not work so hard. Let's do this. So instead of 2023, I'm going to select the current year and data from that month. I'm going to use this again. And for the, the reason I'm making this plot is I want to see if 2023 was an unusual January or not. So I'm going to select the color to be just a plain gray if it's not 2023. And I'm going to make it black if it is 2023. So I can say color. This is the first time we're seeing the if-else function. This is kind of a handy function. So I give it a conditional. So I'm comparing the jth year to 2023. It's going to be true if it's less than 23 and false otherwise. And then I have to say, okay, what should I assign if this is true? I'm going to make this gray. And if it's false, I'm going to make it black. So the way if-else works, you have condition, what gets returned if it's true, and then what gets returned if it's false. So this is going to be gray. Color is going to be gray if it's less than 2023, and it's going to be black if it's equal to 2023. And then I do lines. Lines is a function for adding lines to a plot. Lines operates differently than the plot function. Plot is what's called a high-level plotting function, which generates a new plot. Lines will add something to the plot. So that's what we want. And we'll make it this color. Excuse me. And then close our for loop. Okay, so let's do that. We've set up the empty plot and we run the loop. Okay, and we get that. So now we can look at the plot and say, okay, it does get down to minus 30, so we should probably leave that, but it really doesn't get much higher than 20. So maybe we can set this to 20. And then since it's code, it's really easy just to rerun it. Okay, so that looks like that. So now we can see the gray lines kind of give the range of what's going on typically in January over this time period. And then the gray one is, the black one is what happened in 2023. So you can see it started out pretty warm relative to a typical January, and then was kind of average for a while, got warm again, and then got pretty cold relative to history at the end of January. But not as cold as it can be in January. The minimum over this time period is like minus 30 Celsius, which is pretty darn cold. Okay, so you might decide, oh, I want to make other modifications. I can make the width of this black line. If I really want it to stand out, I can make it wider. So 1 is the default, but 2 will make it wider. Oh, actually, that won't work. I need to make the width I need to do it like this. So width is going to be 1 if it's less than 2023, and it's going to be 2 if it's equal. Okay, so that makes it a thick black line if it's 2023. So maybe that looks a little better. Okay, we can try other things. So maybe I want a little bit of variation in these gray ones, so I can kind of pick apart individual years. That's going to be a little bit hard to do because it's like 18 years of data, but we can try that. So let me show you. There's lots of different color capabilities in R. One of the modern packages for dealing with colors is called Virides. So you can do, let's see, so colors equals, the function is called Virides. And we could say length years. So what gets returned here are a bunch of colors in what's called a hexadecimal format. So each of these is like a code for a color. It runs from like yellow to dark green, or dark green to yellow. I forget which direction it goes. So this, yeah, that means some specific color. And then I can set up my plot the same way. Let's do this. And okay, let's not do that. But the color is going to be colors J. So it's the same exact plot. I am making the 2023 wider, but for the color, I'm just doing the color from this Virides palette. So let's see what that looks like. Okay, so that's kind of cool. So it's kind of hard to see. So this yellow one is the wider one. That's 2023. And then there's some variation in the colors for the other years. I don't quite like that. Let's make the darker one. So we could do these in reverse order. Let's make the darkest one 2023. That looks a little bit better. I don't love that either. All right, here's what we're going to do. We're going to do this. So basically what I want to do is I want to make most of them like yellow green. And then I want to make 2023 really stand out by having it be this dark color. So I need to do, I don't want to do if else. Actually, I can do if else, can I? I got to give it a different name. Color. Oh, okay, I could do this. Colors, J. Okay, so what's going to happen here? Color is going to be, I need to make this color. Color is going to be just one of the first colors, so the corresponding color. This is doubly long, so let me run this. This is running, even though you can't see the names, this is running from yellow to like a deep bluish purple. And so these are going to be like all yellow green colors. So if it's less than 23, it'll grab one of these yellow green colors. And if it's bigger, if it is equal to 2023, it grabs the very last one, which is like a deep bluish purple color like that. Okay, so let's run that. Maybe this will look a little better. Okay, that I like a lot better. So the 2023 really stands out, and you can see some variation, the colors of the different year, and they're actually meaningful. You might want to add a legend to this to say like the yellowest yellow means 2005. and the greenest green means 2022, and then this means 2023. We won't do that now. Okay, what else can we do? We should add a title, maybe. That looks nice. Just for fun, let's do the whole year. So if I want to do the whole year, I don't select the month, and I can't use day. I have to use the day of the year. So day is like the day of the month. Should say day of year. Let's look through. It looks okay. X limit should go from 1 to, let's say, 66 because of leap years. I think that's all right. All right, let's run that. Something didn't work. Oh, there it is. Okay, now we were plotting January before, and so this range was okay. So we need to actually make the upper limit much higher. So let's try 40. I don't know why that's not working. Maybe it's just not running all that code. Okay, that looks pretty good. Oh, the other thing, yeah, did we do this? Yeah, you can zoom if you want to look at your plot, make it a bit larger. So that's our plot. Okay, so that's what a typical, so the green and yellow is like what a typical year of temperatures are like in Ithaca. And then the dark, whatever you want to call this color, dark purple is what's happened so far this year in 2023. So I think there was a kind of a warm period here. Summer was kind of normal, except we got a little bit of a warm period here. And now maybe it's a little bit cooler than normal. Okay, so that's it for this video on graphics and plotting data visualization in R. I really feel like this is just scratching the surface. As you get more proficient at making plots in R, and you want to make them look really professional, you're going to find yourself calling plot with type equals n very often. So you might want to, we didn't cover this, but you might also want to set axes equals false and add your own axis at the specific places you want the tick marks to be. You're going to be setting and then you're going to be adding things to the plot with like the points function, which adds points, and lines function, which adds lines. You'll probably want to add a legend. You want to add text. So you may get pretty complicated code for generating your plots, but that's really what it takes to make it look exactly like you want it to look. Okay, we'll see you next time.